what's the intuition behind the validate phase? What do we do?
That's a lock in the validate.
Yeah, well, we like check if during the time that we were like pretending to do all the work, anybody else was in there stomping on the same stuff that we were stomping on. And if they were, we abort, but if they aren't, we go forward. And then the final phase, of course, is the write phase, in which might even be better just called like the install phase, because in some sense you've done your writes locally, and all you're doing is swapping the local rights for the, putting your local rights on the actual database. Right, so we need to talk for just a minute about what it means to validate our transaction. Okay? And what we want to be able to say is, I'm not even going to get into the terminology. We want to be able to say, our transaction had a set WS. That's the write set, which is the objects our transaction wrote. And it has a read set, the objects that our transaction read. Okay? And really there's three possible cases when we can say our transaction, let's say our transaction is called TJ. Okay? Now let's consider all the transactions TI, such that TI is less than TJ. And what I mean is, let's just imagine every transaction that comes in the system, it gets a number, just as we did over here. Every transaction's got a number. So you're saying, like, consider all the transactions that happened before mine. Or, that entered the system after mine entered the system. Can we say that TI finished before TJ began? And then obviously, if we can, then we know they didn't conflict. Like if TI finished its write phase before TJ began its read phase, obviously they didn't conflict. TJ happened after TI. TJ definitely saw all the writes that TI did, right? Or can we say that the write set, let me just make sure I have this right. It's a little fussy. All right. Does the write set of TI, the intersection of that with the read set of TJ empty, and let's see, T finishes writes before TJ begins writes. Right? So if TI, now see, TI and TJ have overlapped in this case, but the write phases, which are very short, have not overlapped. If the write phases have not overlapped, we know they don't have a write conflict. But we might still be worried about read-write conflicts and write-read conflicts. However, if TJ didn't read anything that TI wrote, that is to say the intersection of the write set of TI and the read set of TJ is empty, they didn't touch it in the same variables, then there isn't a read-read conflict either, right? So this rules out, this is no conflicts. This is no write-write conflicts, and this says no read-write or no write-read or read-write conflicts. Great. There's one left to do, which goes like this. Does the write set of TI intersect with the read set of TJ? And the write set of TI intersect with the write set of TJ is empty. And TI stops reading, ends its read phase. I don't want to work that out. Before TJ stops reading. Okay, so you see what's happening here is that as we go from top to bottom, we're going from they couldn't possibly have conflicted, they were separated in time, so they overlapped but their writes didn't overlap in time, and their reads and writes didn't overlap in value, to they could have overlapped, but they didn't touch anything in common. If you can answer yes to any one of these three things, you can go ahead and commit TJ. If the answer is no to all three, TJ has to be aborted and restarted. So I know it's a bunch of terminology. I felt like you deserve the terminology. An exercise for the class to like think about how this rules out all the kinds of conflicts. Like I don't think we have time to. Yeah, maybe we do. Well, it's trivial in this one, right? So whoever comes second will detect that there are non-trivial conflicts between the read and write sets of the two transactions, right? And so whoever comes second will abort in OCC. Like in a trivial example like this, there isn't too much to show. Yeah.
Can you explain number 3?
Yeah. And look, it's easier to explain in order, right? So like this one says, number 1 says, look, here's TI, and like here's TJ, so you're fine, right? And then it's like, let's imagine that there's a write phase and a validation phase and a read phase. Read, validate, write. Number 2 is saying like, let's see. Our write phases didn't overlap. Like our read phases might have overlapped a little bit, but like our write phases didn't overlap. Oh, and by the way, I didn't read anything that you wrote, so I can't conflict with you. And then this last one's saying, I don't know, buddy. They're kind of like right stomping right on top of each other. I can't say that I wasn't allowed to do a write until you finished doing your writes or anything like that. But I can say that you didn't touch anything in common, right? So this is definitely safe too, because the two transactions are independent. In the same way that like if I get a lock on X and you get a lock on Y, we don't conflict with each other, because we're not touching the same thing. Yeah?
Could you make any arguments for, so when you talked about how whether these sorts of things were implemented from the database level, like the big database, or versus the app specific, is there any sort of reasoning you can do between, like, say you were writing from the app specific and you have the uncertainty of your distributed database, which would be a better method for the...
I don't know. So, it seems to me that you could do both in the app. Right, because you usually think about the locks being very close to the data, and there's good reasons to do that. So you typically think about the locks being implemented by the database. But you can have like a logical notion of the locks in your app, and before going to the database, you could be like, has somebody, well, as long, no, that would work, right? As long as everybody went through your app or something like that. So optimistic probably makes a lot more sense if you have an app where like you have a lot of different copies of that app running on different clients. Because as I said the other day, optimistic concurrency control, when there are conflicts, throws away resources.
Right.
But the question is, whose resources and do you care?
Like the client.
Yeah.
So, I feel that because they both need to lock at some point, it's just harder for me to conceive of how to even reason about obtaining a lock from the client side.
Yeah, no, it's super hard. I mean, I don't know.
Yeah.
I don't know. I mean, so I think OCC would be easier to try to do in the client. It seems like there's still these sketchy race conditions around validation. Yeah.
Do transactions always need to read everything first and then write everything afterwards? Or is there examples like that third one where there could have been reads?
No. So like in your read phase, you could be going back and forth between reads and writes. Like you could go out to the database, read some things, do some conditional writes, go to the database again, overwrite your writes. But the point is that only once and all at once do they actually get like installed on the database. All right, I do want to talk about session guarantees because I feel like this is my last chance to do so, so I'm going to stop this here. This is fun. So this is my bread and butter. This is like what I studied in grad school and what I TA'd on. So I remember a lot of like, if this seems more gorely detailed than the stuff I usually teach, it's because I teach the stuff I know I've learned more recently with broad strokes and the database stuff. So forgive the formalism. Session guarantees. We liked serializability, and we liked, strongly consistent replication because they gave us these guarantees, right? And I kind of did this thing with the databases. Something I would ask in previous versions of this class is like, well, what's so great about guarantee? Anyway, like who cares about the guarantees? I think one argument I made today was that if you get the guarantee, there's all this code that you don't have to write. Code that you don't have to write over and over again every time you write an application that sits on the database. That's a pretty good one. But I think in general, if you imagine a world in which violations of serializability and violations of strong consistency could happen, it's still worth asking yourself in the context of your particular application, from the point of view of the sessions and the clients using the application, do you care? And so what are the two things that can go wrong in databases? Well, if we don't have strong consistency, we could have stale reads, right? We could read some data too late, right? Or read data too old. And we could have write conflicts. And those are bad, right? Well, depends. I mean, a write conflict certainly is only bad if somebody sees it.
Right.
So if my anti-entropy clears up all the write conflicts before anybody reads them, do I care?
No.
Maybe not. Stale reads only matter if my application cares about the recency of the data. Let's look at a couple of examples. Let's imagine that there's a server Alice and there's a server Bob, and they're partitioned from each other, or maybe they're not partitioned. They're just far enough away from each other that they might as well be partitioned. But when Alice knows something, Bob doesn't instantaneously know about it, right? So let's say some client, Clarissa, comes along and says, let's say x is 0, right? It's classic. Clarissa says, I don't know, x is 1. And then almost immediately, but after, in real time, whatever that is, client Bob, the beholder, comes along and wants to read x, and he gets back 0. Oh, it's bad because it was stale. But who cares? I mean, like, if this were a messaging app, imagine you texted me, and then almost immediately after you texted me, I look at my phone, the text's not there. And then I look again, there it is. Who cares, right? Bob didn't know that he was supposed to read 1, or for that matter, that 1 was even the most recent value. The only way he would have known that is if Carol or Clarissa got on the telephone with him. That would be what we call side channel, right? Lamport talks about that in the context of causality, right? If you get on the phone, you might break the system because the phone, you're not able to push your clocks into the phone, right? Okay, so you see what I'm saying, though? We can imagine a great many apps where this kind of stale read anomaly is not problematic at all. In fact, almost all apps, I wouldn't care. I'd rather get a quick answer than wait for the replication. On the other hand, if Clarissa says x equals 1, and then she is redirected to this replica, and she reads x equals 0, that's unfortunate, right? Because she knows what the most recent write to x was. Right? So, and a weakly consistent system could have either of these behaviors happen if we haven't done anything to prevent it. One of them is like really bad, and one of them isn't. So the idea behind session guarantees is, let's try to enumerate the things that are really bad and separate them out from the things that aren't that bad. It's going to turn out that strong consistency gets us all of the session guarantees, but it gets us a lot more and it pays a lot more than we need to get them. So this one right here is a violation of probably the simplest and cheapest imaginable session guarantee. Read your goddamn rights. Right? And this is just saying that, like, intuitively, a violation of read your rights is a violation of causality. But not every violation of causality is a violation of read your rights. And read your rights is sort of like the bare minimum that you would want from causality. Yeah?
Would we have something like vector clocks attached to that so that Coraline can tell the difference between that violation and somebody else just...
Yeah, you totally could. We could do better than that for this one. But like TLDR, you can use vector clocks as the mechanism to get all of the session guarantees. It's going to turn out that some of them you can get with even cheaper mechanisms than that.
I guess my actual question was, how does Coraline know that that's actually a violation and not...
She wrote it.
Well,
and not that somebody else came along and then someone else wrote it afterwards. How does she know?
Oh, well, because if, for example, x equals 0 had some real old vector clock on it,
Okay, great.
and for example, and then now she's got some vector clock that's like 1.0, and it gets out here, and it's like, oh, this is definitely stale. Right, this is akin to what you're looking at in your assignment, except I very carefully in your assignment didn't ask you to enforce read your rights. Right, so you're implementing a version of causal consistency that's pretty damn weak, because it does not enforce read your rights. I did that on purpose to make my life easier. Okay. But you're absolutely right. If I used causal context, I could prevent that from happening. I could actually prevent that from happening in an even more easy way. How? I could trivially enforce read your rights. How? Yeah.
Buffers.
Say again?
Buffer.
Yeah, but what do you mean by buffer that?
Put it on core line.
Yeah, I mean, like, if all I had to do was enforce read